Our presenter tonight is Peter Flynn. Peter is an educational technology consultant for TI Australia and has been involved in mathematics education for over 30 years. He has vast experience in sharing his knowledge through mentoring and presenting at conferences. So thank you for sharing your expertise with us tonight, Peter.
Hopefully you can see my screen. So welcome. VCE Specialist Mathematics has a new study design from 2023 to 2027 as the period of accreditation, and vector calculus remains part of the syllabus with a small tweak from the previous study design. So welcome, my name's Peter. In this presentation, I've used the snipping tool to garner a couple of diagrams from the Cambridge Specialist Maths Unit 3 and 4 textbook. So the study design in 2023 to 2027, there's 3 dot points that relate to vector calculus. The first one is getting students to look at position vectors as a function of time and sketching Cartesian equations or the corresponding path given the vector function. Ellipses and hyperbolas in Cartesian or parametric form. Note that parabolas are not mentioned there. Topic also includes the position of 2 particles, each described as a vector function of time, and to study whether their paths cross or if the particles actually meet or collide. The third dot point is really the calculus part, differentiation and anti-differentiation of a vector function with respect to time, and applying vector calculus to motion in a plane, which is 2 dimensions. And that was where the study design was limited in its previous incarnation. This time, they've gone back 2 study designs and now allowed study in 3 dimensions. So we have 2 dimensions and 3 dimensions for the vector calculus part of these 3 dot points. So first of all, we'll just briefly look at some preliminaries. We'll look at a definition for position vector as a function of time, and also a definition for vector calculus and the quantities, the vector quantities, velocity and acceleration. So in 2 dimensions, when a particle moves along a curve in a plane, so the particle's moving along the curve there denoted in red, its position is specified by a vector function of the form vector r of t equals x of t I plus y of t j. Correspondingly, when a particle moves along a curve in 3-dimensional space, its position is specified by a vector function of the form vector r of t is xt of I plus yt of j plus zt of k. I, j and k are direction givers, and they'll have a magnitude of 1, so they're unit vectors. And again, we've got the particle moving along a path or a curve there denoted in red, and you can see the position vector there. We can go a little bit further and talk about velocity. So if we consider a particle moving with position vector at time t, given by r of t is x of t I plus y of t j plus z of t k. Now, under the condition that x of t, y of t and z of t are in fact differentiable, then now note here that I've used Lagrangian notation. In the textbook, you might see dots which use Newtonian notation for the derivative. So here, the velocity r dashed of t is given by x dashed of ti plus y dashed of tj plus z dashed of tk. This is the velocity or the rate of change of position vector, and importantly, it gives the direction of motion at any time t. And there's a lovely example of that, that at point P we can see there the velocity vector r dot of t. It's specifying the direction of the particle at that particular instant in time. And correspondingly, acceleration, consider a particle again, same position vector. And basically what we do is we differentiate x of t, y of t, and z of t twice to form the second derivative of r of t. And this is the acceleration vector, or the rate of change of velocity vector. So when you're performing differentiation and anti-differentiation, we call it you're differentiating component-wise or anti-differentiating component-wise, essentially. Okay, so let's have a look at quite a straightforward example. This is an example that could appear on exam 1, and it's quite well within the realms of capable students' by hand capabilities, but we'll also have a look at it from a TI-Nspire CAS viewpoint, with the view to looking at how vectors, position vectors, velocity vectors, and acceleration vectors can be dealt with on a TI-Nspire CAS in, say, exam 2 multiple choice or extended response. So if I was a teacher doing this example, I'd probably do this twice, but privilege by hand techniques. So we have a particle moving so that its position vector r at time t, where t is greater than or equal to 0, is given by r of t is 3 cos 2ti plus 3 sine 2tj. And what you want to do with students is you want them to think about, right, what path might that particle trace out or move along? And, you know, if you become familiar with all the different forms, students should be able to anticipate that this particle is going to move in a circle. So there's 3 parts to this question. Show that the particle moves in a circle and find the Cartesian equation of its path. Show that the particle moves with constant speed. And finally, show that the particle's acceleration has constant magnitude and is perpendicular to the direction of motion of the particle. I might say that so far, all these pages that you've been looking at, if I just scroll back through, these are all notes pages. And the notes application is one of the powerful applications within the suite of TI-Nspire applications. And so far what you've seen is that you can obviously, as the name suggests, you can write notes. But you can also insert these objects called math boxes. And so I've expressed that position vector there inside a math box. It's currently inactive, but you can activate them and perform mathematics within these objects. So just quickly as an aside, if I just press enter and I press menu, 3 for insert, and then 1 or enter for math box will insert a math box. And also note there that the shortcut is Control M. So some of you might be familiar with the notes application. It's not quite the focus for tonight. That was basically just as an aside, if anybody was curious about how these pages are being produced. And of course, what I'm doing here, you can prepare lessons and then show them on the TI-Nspire software to the students, just like I'm talking to you now. This is basically a PowerPoint, if you like, or you know, a handout. So let's go to the next page, notes application again. And this is really just a by hand primer. So I'm not really going to be talking about CAS here. I don't think really students should be using CAS here in part A, but the traditional approach is to form our parametric equations, x of t and y of t. And in this instance, because we have x as a function of cos and y as a function of sine, we can square both sides and we can exploit the Pythagorean trigonometric identity. Cos squared theta plus sine squared theta is always equal to 1. So if we square both sides of 1 and 2, we get x squared is 9 cos squared 2t and y squared is 9 sine squared 2t. And then if we add them together, we get x squared plus y squared equals 3 squared or 9. multiplied by cos squared 2t plus sine squared 2t. We know that equals 1, so therefore we get x squared plus y squared equals 9, which is the equation of a circle with centre 0, 0. I think it's always a good idea to specify the domain. And so this particle is moving from -3 to 3. So that's essentially part A. Now, part B is quite straightforward by hand, but let's start to bring in the capabilities of TI-Nspire to answer parts B and C. So we move now to page 3.3. And the first point that I want to make is that we can graph this pair of parametric equations, and we can see quite clearly what the particle's path actually is. So this is a split page. The top part or top strip of it is a notes page, just with the heading there. And here we have a graphs page. Now, if I press tab, notice that I'm in the parametric mode of graphing. So if I press escape, I'll show you how to get into that. We press menu, then press 3 for graph entry edit. You've got various modes for graphing. And the mode that I want to tap into, it's not function. If it was function, it would come up f1 of x equals, if it was scatter plot, you know, it'd be x1, y1 with arrows. But we want parametric number 4. So if I press number 4, now the reason why it's gone to x2 of t and y2 of t is because we have some parametric equations already in x1 of t and y1 of t. So if we go up with our navigation pad, what I've done there is I've entered 3 cos 2t for x1 of t and correspondingly 3 sine 2t for y1 of t. I've also stated that t is going to lie between 0 and 2 pi, and there's our t step, which ends up being a multiple of pi, quite a small one. And so then we graph that, and we can see quite clearly that it's a circular path. Now, just a little tip about window settings. If you know you've got a circle and you want to see it as a circle, and if we press menu and go to window zoom and scroll up or down, utilize the zoom square command, and what that'll do is it will show the path as a circle. If you have, if you like, a window that isn't square, students could be misled and that the circle doesn't look like a circle but looks elliptical. So I would use the zoom square command when you know that you want to graph circles. So that's basically what it looks like. There is a trace feature as well. So if we press menu and then 5 for trace, and then 1 or enter for graph trace, you might see a path plot there. I'll show that a little bit later. But here, this tells you where the particle starts. So it starts at the coordinates 3, 0, and then by pressing arrow to the right there on the navigation pad, we can see that this particle is traveling in an anti-clockwise direction, and it gives you the particle's coordinates at a particular time t. So to get out of the graph trace, press escape, press menu 5 for trace. You can change the step either from automatic or to an increment of your choice. If you want to change it to say 0.2 or 0.3, just type it in and then press OK. Okay, so that's pretty much establishing from the mathematics that this particle's moving in a circle, so it's exhibiting circular motion. Let's have a look now at part B. And because I've been teaching, it said on the spiel for over 30 years, I've got Alzheimer's. So if I go back, part B says, show that the particle moves with constant speed. Okay, so again, small strip at the top, notes application, just showing you that we're going to look at part B. Here we have a calculator application. And what I've done here is I've specified or assigned R of t to be 3 cos 2t, 3 sine 2t. So let's get a handle upon what I'm doing here. So R of t is essentially the position vector. You can use define. My predilection is for the assign command. See there, it's colon equals. The way to access that from the keypad is to press Control and then the symbols template. You can see that it's quite small, colon equals in blue above that button. And so if we say R of t, so R, comma, or not comma, but open bracket t, and then come out of the bracket there, Control symbols template, and then we use the square bracket and then type in 3 cos 2t and then a comma. So I've just entered the I component and then 3 sine 2t and then press enter. The comma disappears after you press enter. So that's basically how I assigned the position vector to be R of t. It's already up there, so I can just get rid of what I just typed in. The next entry line, what we can do is, now if you're not familiar with the shortcuts, there is a shortcut for the derivative. If you press Shift minus, that brings up the derivative template, and then you can just put in dt there and then R of t. Notice that the R is bold and not italicized, and that's a good sign. It means that we've assigned R of t to be that position vector, so that's fine. And we press enter, and there we get the corresponding velocity vector. And so the corresponding velocity vector, and again, this should be well within the realms of student by hand capabilities. It's -6 sine 2ti plus 6 cos 2tj. And if we go back to the question's not asking us for velocity, it's asking us for speed, and show that the particle moves with constant speed, which means there shouldn't be any functional dependence upon t. So this next entry that I've highlighted here, that could seem a bit weird. What's this norm command, and what's it mean, and where do you find it? So speed is the magnitude of a velocity vector. So basically we're working out the magnitude of the velocity vector. It's performed using this norm command. Where do we find norm? Well, back in the day, he'd be an overweight fellow sitting on the couch in Life Be In It ads. But today, you press 7 for matrix and vector, and then 7 for norms, and then 1 or enter for norm. So that's how you find norm. And the other thing is, the students, they're very adroit on the keypad. They could just type in NORM, and they obtain that command, really quickly. This is an example of a nested command as well. So we've got norm, and then open bracket, go up and grab the derivative of R of t, and then press enter. And so the speed is 6. It's constant. There's no functional dependence upon t. So we've been able to show that. I think it's worthwhile also going through the steps with the students by hand there as well. And part C is show that the particle's acceleration has constant magnitude. So again, note of functional dependence upon t, and show that it's perpendicular to the direction of motion of the particle. So that last part means what we need to do is we need to form the dot product of the acceleration vector and the velocity vector. And for perpendicularity, we need to show that those two are equal to 0. Again, I would go through by hand there with the students. Let's see what happens on a CAS. So we go to the next page. And basically, to find the second derivative, if you press the catalogue and then go to number 5 for the symbols and template, that's where you can quickly access the second derivative. So I've just pasted that in there. So the second derivative of r of t, so it shouldn't be surprising that it's -12 cos 2 ti minus 12 sine 2 tj. We had a cue about how to find the magnitude of a vector in the previous part, so we're going to use the norm command. So norm of r double dashed of t, of vector r of t, gives us 12, which shows us that the acceleration is of a constant magnitude. And the final line here illustrates the use of the dot product. So the general syntax for dot product is, and I'll show you where to find dot product in a moment. I mean, first of all, you can just type it in. There you go, that comes up nicely. It's dot p, as you can see there, and then it's vector 1, comma, vector 2. All right, so in this instance, it's a dot product of acceleration vector and velocity vector. So in mathematical terms there, that's r double dashed of t dot r dashed of t. Where do you find the dot product? Press menu, go to 7, matrix and vector, scroll up or down till you get to vector, press the arrow to the right, and you can see number 3 there is dot product. So that's how you find that. And we perform the dot product and we do get our anticipated answer of 0. And so therefore, we go back to the wording of the question just to be careful. We have shown that the particle's acceleration is perpendicular to the direction of motion of the particle. Okay. On problem 4 is a similar example to the first one, which we won't cover today. But so there's an example of that's using zoom square again, and we're very confident that that's an elliptical pathway. So we'll just make that note on the way through. Second dot point in the study design basically can be distilled into, do these particles collide or not? So let's have a look at the first example, where we're going to bring in a bit more dynamic nature or capabilities of the Nspire here, so it's not as symbolic as the first example. So the motion of two particles are given by these two position vectors. We can see there where t is between 0 and 2 pi. So the question, there's two questions. Do the two particles collide? If they do, determine the points of collision and the time of collision. Well, the great thing is if they don't collide, then we don't need to answer part B, of course. So if you're lazy, we're hoping they don't collide. So let's go to the next page and let's see what's going on here. Right. So using parametric mode graphing, which I showed with the previous example, we've got the parametric equations for particle 1, and they're x1 of t and y1 of t. And we've also got a second position vector, r2 of t. And we've graphed the parametric equations x2 of t and y2 of t. It's nicely color-coded. And I've also used zoom square here again. So one particle is exhibiting circular motion by the looks, and the second particle is exhibiting straight line motion. We suspect simple harmonic motion, but we want to determine whether these particles collide or not. Now we can undertake a symbolic analysis, but the first port of call that I think we should try to make as teachers is see if we can animate it, visualize it, and see whether they do in fact collide. Excuse me. Now, the definition of collision is that they should be at the same point at the same time. It's quite possible when you study two particles moving in two-dimensional space, they may certainly be at a particular point. They may, they may cross a particular point, but they may cross them at different times. And in that instance, they don't collide. So let's press menu, go to number 5 for trace. Now we'll bring in, we won't use graph trace here. We'll go to number 4, which is path plot, and we'll choose number 2, parametric. And so, well, quite a bit's gone on here. Looks as though we've got an animation button. We've got particles there at their initial positions. So we can see that particle 1 is going to start at 3, 0. Particle 2 is going to start at 1, 2. And so when I press the play button, what's going to happen is we're going to have 2 pi seconds worth of animation, and we try to determine whether in fact these two particles collide or not. So we start the animation, and so particle 2 is just moving up and back the straight line, and particle 1's moving in a circle. Now, I'm thinking that these particles don't look as though they've collided, and we can back that up mathematically. So it's nice to simulate it. They certainly will have shared it's possible that they shared that point there, but not at the same time. All right, so we don't think these particles have collided based on this simulation. Press escape, get out of that. And we can now go to a more formal analysis, and not really showing you anything different from the basic mechanics that I've shown in previous examples. We're now just building on what we did in the first example. We can assign R1 of t to be x1 of t I plus y1 of tj, essentially. Now, because x1 of t and y1 of t, we're in the same problem. So in page 5.3, that x1 of t and y1 of t, they've already been defined on page 5.2 in the graphs application. And correspondingly, R2 of t is x2 of t I plus y2 of t j. Pardon me. So I've assigned those two. And what you can do is you could say, well, all right, why don't we solve x1 of t equals x2 of t for t, and we can restrict t to between 0 and 2 pi. So if I go down and then come up, we can see that they certainly have the same x coordinate at quite a few values of t. So there's one, there's another one, there's another one, another one, another one, another one. And we can do the corresponding solving of y1 of t, setting y1 of t and y2 of t to be equal to each other. and solving for t with the restriction that t lies between 0 and 2 pi. And so they have the same y coordinate for particular values of t. And what you can do is you can note all these t values down and then compare them. And what you'll find is that there are no common t values in these two solution sets. And that can be verified when you actually set R1 of t equal to R2 of t. So these are vectors. Set them equal to 0. Set them equal to each other, my apologies. And look for any common solutions there between 0 and 2 pi, and comes up with false. And so that's that, and that match up with what we saw in the animation. So these two particles do not collide, right? So we've been able to see it via an animation, and then we've been able to look at it from a much more analytic point of view. So the answer to part A is no, they don't collide, and you can provide the evidence for that, and then we don't have to answer part B. We move to colliding particles number 2. Now you're not going to believe this, but there's a very big chance that these particles collide. I suppose that's just the way we set things up when we teach. So here we have two different position vectors, t is greater than or equal to 0. Do these two particles collide? And if they do, determine the points of collision and the time of collision. So what we've done here, if we go to the next page, again, so position vector 1 is, we have the parametric equations there, x1 of t and y1 of t. So we've got 2t minus 3i, and we've got t squared plus 10j there. And for particle 2, the parametric equations are x of 2t is t plus 2, y2 of t is 7t. So we've got t plus 2i plus 7t j. There we go. Okay, so looks as though particle 2 looks as though it's moving in a straight line. Particle 1 is moving in a curvilinear fashion. There is a point of intersection there, but we need to determine whether they cross that point of intersection or they meet there at the same time. So we can set up another animation. So we press menu, then go to 5 for trace, 4 for path plot, 2 for parametric. So we're ready to go. Now, I'll see how I go here. I'm probably not going to be able to stop them at the right times, but before we start, their initial positions. So position vector 1, it's starting at -3, 10. It's on that curvy pathway. And position vector 2 is starting at 2, 0. So we're away. Right. I'm just going to do it again. I was a bit slow then. I wanted to stop at 2. If I don't get it this time, right. Stops at 2. Now, notice that particle 1 is at position 114 and particle 2 is at position 414. They are at different x coordinates. They have different x coordinates, but at the moment, at that instant, they share the same y coordinate. Let's continue on. Right, so they're approaching each other. It's getting very exciting. They're getting very close to each other, very close. Voomp, done it. At t equals 5, they share the same position. 735. And so we can conclude from this animation that that is a point of collision. We also have the time of collision, and we can play the animation out, assuming that they've survived the collision. So press escape, and we go to the next page. It's quite a similar analysis to those two particles that didn't collide. So I've assigned R1 of t to be x1 of ti plus y1 of tj, and R2 of t to be x2 of ti plus y2 of tj. We set the x coordinates equal to each other, so the parametric equations x1 of t and x2 of t, we set them equal to each other and solve for t. We get t equals 5, and that rings true. And when we solve, or when we set y1 of t and y2 of t to equal each other and solve for t, we get t equals 2 or t equals 5. So we've rationalized the t equals 2 situation. They shared the same y coordinate, but they had different x coordinates. What we're after is we're after a value of t that satisfies both those two equations, and the value of t that does satisfy both is t equals 5. So we can substitute t equals 2 into both expressions there for the position vector, and that was on our graph screen. 114 was the coordinates at t equals 2 for the first particle, and the coordinates 414 at t equals 2 for the second particle. And we can set, now when we did it for the particles that didn't collide, when we set R1 of t to equal R2 of t and solve for t, we got a false. But this time we actually get the shared t value there, the common t value, t equals 5. And then substituting t equals 5 into both R1 and R2, and we get that point of collision 735. Okay. Final example is we looked at some differentiation. Now we should look at anti-differentiation. It's a little bit more fiddly. If I was doing this example with students, I'd do this both ways and probably privilege by hand. The acceleration, but I think when I say that though, if the derivatives or antiderivatives, depending upon what you're doing, if they are starting to become quite complex and it appears as though that it's more efficient and accurate to do it with the CAS, then that's it's accuracy and efficiency that are my guidelines as to how I shape my teacher practice. And that accuracy and efficiency also should shape what the students, what their approaches are in the exam, because in exam 2, if they try and do everything by hand, they won't finish it. And if they try and do everything by CAS, they won't finish it. So you've got to make good decisions, and they've got a year to learn and prepare for making those good decisions. So acceleration of a particle at time t is given by that one there. So 3 root ti plus 2t plus 1j minus 4k. Find the particle's position at time t if its initial position is 1, 1, 1, or its initial position vector is I plus j plus k, and its initial velocity is 5i. So it's only moving in the x direction, right? So makes sense that if we go to anti-differentiate twice, we have 2 initial conditions. Okay, so this will take a couple of minutes to talk through. I'm just looking at the time as well. By the time I talk through these, it should be about just after 8:15 and we finish up. So I have assigned the acceleration vector. So I've assigned it to be RA, and assign is by control symbols template. And so when I'm assigning that, these components are separated by commas. Notice that I'm using row vectors, basically actually to save space. I know that they're more commonly described as column vectors, but that ends up taking a lot of space up on the screen. As long as students realize row vectors, column vectors, it doesn't matter as long as we're looking at I component, J component, K component. Okay, so now I've assigned RV, so this is the general velocity vector. I've assigned that to be the indefinite integral of the above vector with respect to t. So what you'll see there is if I anti-differentiate 3 root t, I get 2t to the 3 on 2. Anti-differentiate 2t plus 1, I get t squared plus t. Anti-differentiate negative 4. These are all with respect to t. I get negative 4t. But we know that when we anti-differentiate, we need to add a constant. And because we're dealing with vector functions, the constant is a vector. So this is where I've assigned the first constant to be C1. And I've assigned it to be, now that's a representation, that's the initial velocity vector there, right? So that's basically R of, in here is R dashed of naught equals 5i. And then transposing, basically subtracting the velocity vector when t is 0. So our first constant of integration is 5i, basically. Now what we do is we anti-differentiate again. So I've assigned R of P, so P being for the position vector. I've assigned that to be the indefinite integral of RV plus C1. So it's those two added together. And you can see that there. If you add those two together mentally and then anti-differentiate, there's your I component, your J component, and your K component. You now apply the initial condition that R of naught is I plus J plus K. So in TI-Nspire notation speak, I've assigned the second constant to be 1, 1, 1, and then subtracted from it R of P at t equals 0. And so that is basically our final constant of integration. And then we add RP and C2 together. And therefore, the acceleration vector is that I plus that J plus that K. Alternatively, what you can do is you can use the differential equation solver 3 times separately on each component. So that's the syntax for the I component there. So x double prime is 3 root t, and x prime of 0 is 5, and x of 0 is 1. Independent variable, dependent variable. So that's the I component for the position vector. And then the corresponding differential equation and conditions for the J component and the K component. To find the differential equation solver, you press menu, 4 for calculus, and then scrolling up or down, you find the differential equation solver. If you've got the most up-to-date or very, very recent operating system, it comes up as a dialog box. If you're working on, and I can't remember exactly where the cutoff is, if you're working with an operating system from a little bit further back, then you don't have a dialog box. So really quickly, the equation, put in x. If we go to our punctuation marks, don't choose that. That means something different. What you've got to do is you've got to choose prime once and then again, like so. And it was equal to 3 times the square root t. So independent variable is t. dependent variable is x, and one of the conditions was x. Then go to the punctuations and then prime, and then open bracket 0 close bracket equals 5, and another condition x open bracket 0 close bracket equals 1. Press tab to highlight OK, and then press enter, and hopefully we've entered it in incorrectly there, which is 2 words rather than 1 word incorrectly. So x double prime is 3 root t, and x prime of 0 is 5, and x of 0 equals 1 comma t comma x. Press enter, and that's the solution to that differential equation. Okay, so thanks very much for joining us for this webinar. That's all I wanted to show this evening. A little bit nuts and bolts. Wanted to show you how to assign or define a vector, work with it numerically and also symbolically in terms of differentiation and anti-differentiation, which is the vector calculus component, and also wanted to illustrate how you can study particles moving in the plane and whether in fact they collide or not using animation or simulation. So back to you, Emily. Thanks very much for watching, and we'll catch you again next time. Bye.
Thanks for that insightful presentation, Peter. If anyone has any questions for Peter, now's the time to ask. Otherwise, thank you all for joining. I hope you took something out of it, and I hope you have a nice night.